Welcome to The Explainer. Today, we are stepping right into the shoes of a biological detective. I want you to imagine having an evidence board, but instead of tracking timelines or suspects, it literally tracks the very code of life across multiple generations. That is exactly what a genetic pedigree is. It's this incredibly powerful tool that geneticists use to visually trace how traits are passed down through a family bloodline. So, it really makes you wonder, right? Can you predict the future hiding in your family tree? Our family histories are essentially intricate mysteries just waiting to be solved. They're written in this secret genetic language, and once you actually know how to read it, well, you can trace physical traits, anticipate hidden health risks, and even solve biological puzzles that span decades. Okay, let's dive into this. Here is our investigation plan for today. First, decoding genetic family trees. Second, the pedigree investigation process. Third, solving inheritance mysteries. Fourth, advanced clues and curveballs. And finally, clinical stakes and consequences. Moving into Section 1, decoding genetic family trees, or learning the secret language. Now, the standard pedigree legend is the universal language of genetic analysis, and honestly, it is incredibly elegant once you get the hang of it. The whole thing starts with simple geometry. Circles always represent females, and squares always represent males. Now, when you see a shape that's completely filled in with a dark color, that flags an affected individual, meaning someone who's actively expressing the specific trait or genetic condition we're tracking. Blank or unfilled shapes, those are unaffected individuals. And those lines connecting everyone? A horizontal line between a circle and a square means a marriage or mating, and the vertical lines dropping down from that connect the parents to their offspring. Oh, and those offspring are always arranged from left to right in their natural birth order. Pay attention here because there's a very specific, pretty rare symbol you need to watch out for on these charts, the double horizontal line. This denotes a consanguineous marriage, which basically just means a marriage between relatives. So why is this such a massive clue for us genetic detectives? Well, because related individuals share significantly more of their alleles by descent. This drastically increases the probability that their children will inherit two identical rare recessive alleles, one from each parent. Basically, seeing that double line immediately tells a geneticist, hey, watch out for an elevated risk of autosomal recessive disorders. All right, Section 2, the pedigree investigation process, or interrogating the evidence. Just like a detective interviewing witnesses at a crime scene, we have 4 absolutely vital interrogation questions we must ask of every single pedigree we look at. First, does the trait skip generations or does it pop up in every single one? Second, are males and females affected equally or is there some kind of noticeable gender bias? Third, can completely unaffected parents somehow have affected children? And fourth, do affected fathers transmit the trait directly to their sons? By asking these exact questions in order, we systematically narrow down our list of genetic suspects. Now, what's really interesting is how these 4 questions form this ruthless visual elimination flowchart. Take a look at question 1 at the top. If a trait skips generations, boom, we can immediately cross dominant right off our list, because dominant traits simply don't hide. If it doesn't skip, well, dominant remains a highly plausible suspect. From there, we just move down the flowchart. Answering yes or no to the sex distribution and transmission patterns systematically eliminates autosomal, X-linked, dominant, or recessive possibilities, until literally only one logical conclusion remains standing. Let's put this into practice. Section 3. Solving inheritance mysteries. Cracking the case. Let's lay out our initial clues for a case involving polydactyly, which is the presence of extra fingers or toes. Check out our field notes here. Clue number 1, the trait appears in every single generation. Clue 2, there's an equal distribution between males and females. Clue 3, every affected individual has at least one affected parent. Now, look at the balance of these clues. What inheritance pattern do you think this points toward? Bingo. The evidence points straight to autosomal dominant inheritance. Because the trait is dominant, it just takes one single P allele to cause the extra fingers to express. You can literally trace it visually, right down the family tree through generations 1, 2, and 3. Notice how it boldly shows up in every generation, and both squares and circles are shaded in roughly equal measure. Since it only takes one dominant allele to show up, it just doesn't hide silently in the background. Let's try another one. Time to pause and predict. What if you saw a pedigree where affected individuals appear only in generation 3, the grandchildren, but both the parents in generation 2 and the grandparents in generation 1 are completely unaffected? What's the pattern there? Think back to our flowchart from earlier.
Since the trait is hiding entirely for 2 whole generations and then suddenly popping up, this generation's skipping strongly points to a recessive inheritance pattern. The parents and grandparents, they were just carrying the genes silently all along.
Moving on to Section 4, Advanced Clues and Curveballs, Penetrance and Misconceptions. Now, I do have to warn you, biology isn't always just simple, clean math. It's organic, it's messy, and sometimes the visual clues in a pedigree can be incredibly misleading if you don't know exactly what to look for. For example, let's debunk a huge misconception right now. A lot of people think that if a trait skips a generation, it automatically means it's autosomal recessive. But that is a trap. Actually, both autosomal recessive and X-linked recessive traits can skip generations. To know for sure which one it is, we absolutely must look at the biological sexes. If it's autosomal, males and females are affected equally. But if it's X-linked recessive, you'll see a very strong male bias, with the trait often transmitted silently through unaffected carrier mothers directly to their sons. Here's another curveball for you: half-filled symbols. You might see these and assume, oh, a half-filled circle or square always means a heterozygous carrier. You know, someone who silently carries a recessive gene but doesn't show the trait. Actually, scratch that. It's not always true. While they often do indicate carriers for recessive traits, they can also represent mildly affected individuals in dominant traits. Half-filled shapes simply represent an intermediate status. You really need the context from the rest of the chart to decode them properly. And this brilliantly illustrates our next point. Notice the distinct color gradients here? This brings us to the advanced biological concepts of penetrance and expressivity. Sometimes a person has the exact disease genotype, but the trait is totally invisible on them. That's called incomplete penetrance, something we sometimes see with BRCA1 cancer risks. Or, as you can see with the different shades of red, individuals might have the exact same genetic mutation, but express it physically with vastly different severities. That is variable expressivity. The gene is absolutely present, but the way it presents in the real world, that exists on a spectrum. Bringing it home with Section 5, Clinical Stakes and Consequences, the Real-World Impact. So we've been playing detective and having a lot of fun decoding these charts, but accurately interrogating these pedigrees, it is not just a puzzle game. It is a high-stakes matter of life, health, and extreme medical precision. When you look at how this is applied clinically in the real world, it's pretty staggering. Genetic counselors use these exact charts to make life-altering medical decisions. By analyzing a family's pedigree, they can mathematically calculate recurrence risks for future pregnancies. For instance, they can figure out if a child has exactly a 50% chance of inheriting a severe condition like Huntington's disease. Or they can pinpoint exactly which family members need targeted preventative screening for BRCA1 breast cancer mutations. The pedigree tells them precisely who is at risk and who needs early, life-saving intervention. So the crucial point here, and you can see it highlighted by the dramatic incorrect labels, is that mistakes have consequences. If a genetic counselor misreads or misinterprets just a single symbol, say confusing a carrier female symbol with an affected female symbol, the entire investigation collapses. Just one simple visual error cascades into a total disaster. We're talking inaccurate genetic counseling, completely wrong recurrence risk calculations, and inappropriate or even harmful testing recommendations for the family. In this field, visual precision is absolutely everything. We've really seen how incredibly powerful the secret visual language can be, haven't we? From systematically solving biological mysteries to literally saving lives through highly targeted preventative medicine, the pedigree is an absolute masterpiece of scientific investigation. It kind of makes you look at your own family history of it differently now, doesn't it? So what hidden genetic clues are waiting to be uncovered in your own family tree? I highly recommend you grab a notebook, start drawing some circles and squares, and you know what? You might just become your family's very own genetic detective.